So Bruno's talk is titled Raman Spectroscopy in 2D Materials, Exciton-phonon, Double Resonance, and Polarization.
So can you guys hear me, right? Yeah, okay, great. So just okay, just put it in my pockets better. So I'm back, but this time right on the other side. So thank you for the organizers, by the way. I know I'm one of them, and thank you for being here watching this talk as well. So during the week, since last week actually, I was kind of struggling a little bit about what should I talk. I work with optical spectroscopy, and one of my works involves Raman spectroscopy. However, I also work with photoluminescence, nonlinear optics. However, some collaborators were here last week, so I decided to talk about Raman since we had actually the tutorial about group theory and also Pedro's talk this morning. So, okay. So the outline of my talk will be basically involve these works. So the first part involves symmetry-dependent exciton-phonon coupling, where we analyze the MOS2 first-order modes and how they are coupling with the orbitals that are associated with the excitons. Then these next two works over here, I'm talking about double resonance process. More importantly, I prefer to call, in this case, intervalley scattering. This work was a collaboration with the theory, which was the DFT calculation was performed by Dr. Wang. Now he's a postdoc, and it was at Penn State. Duran was there. And okay, moving on. So sorry about that. So, and the second part I'm going to talk about as well, how the double resonance bands can change when are changing the temperature, which is basically try to map the dispersive behavior, not when we do not have too many laser wavelengths. And I'm going to also show some results on single layer granular diselenide. Okay, sorry about that, guys. And I'm gonna show some resonant polarized Raman spectroscopy results that we are actually performing on the anisotropic DMET. The paper is actually in preparation. And the motivation to show these results is basically from last week, where Eric Popper was mentioning some issues that we find at the literature. And here, it is trying to demonstrate that you need to do your polarized Raman correctly in this kind of sample. So when I talk about intervalley scattering or Raman, we know graphene, and we already learned this in the morning. So this is a Raman spectrum of graphene. So here we have the G-band, and it is a one-phonon process, as we learned this morning, and the G-band is related with the in-plane modes, in-plane vibrations in the graphene lattice, and we have the 2D band, which is a two-phonon process, or intervalley scattering between the K and K prime points. And the momentum conservation, in this case, it satisfies because we have two in-plane transversal optical phonos participating in the process. So the most interesting thing about graphene is that it is always in resonance in the visible range. What does it mean? As Pedro talked this morning, it means that when I change the excitation energy from red to, infrared, very close to the UV range, this would be around 458 nanometers, we can see that the 2D band starts to increase its, change its position. increase its frequency and position. And this is related because we are actually selecting different wave factors with different wave sizes when we are actually exciting with different laser energy. And the phonon would be related over here, which involves the TO phonon modes close to the K point. It is important to understand that it is near the K point, not at. Otherwise, we should not be dispersive behavior. So, well, MOS2, we already learned about that. So different from graphene, we have actually 3 layers, thickness, sample. However, if you take a look at the overview, top view over here, we see there is actually like a hexagon symmetry. And we learned that this is actually called 2H phase from the group theory. However, we find at the literature 1H, H here is for hexagon symmetry, which is basically the one, it is in single layer. All right, so depending on the number of layers I will have a different point group. And this is extremely important for Raman especially. So this is just a review, basically. We already learned this during the week, but monolayer MOS2, it is a direct band gap in the red wavelength, around 1.9 eV. And this direct band gap is actually here at the K point. This is just to demonstrate how is the conduction band minimal for monolayer and bulk, just to see that this state over here, right, it is a state, right, between K and gamma, it actually is very quite low, high intensity in this case. How can we see that? Well, we can do very simple experiments. It can be absorption and also photoluminescence experiments. We demonstrate that it has a very strong peak intensity. And when we are actually measuring for different number of layers, we can see other features over here, which is related with the indirect band gap. So one interesting point, it is regarding the absorption experiments, is that, so here at the K point, we have what we call A and B excitons, and close to the gamma point, we have this higher energy, which is the C exon. There is a very nice paper from Lewis group, where they actually demonstrate, they calculated, they made a simulation for the absorption spectrum, and later on, they're considering the quasi-particle lifetime, and they noticed that they can reproduce the experimental results. So the interesting contribution, in my opinion, especially since I work with Raman, is that they can see how is the symmetry of the excitons. In this case, the A and B exciton reflects the MEO ds square orbitals, and the C exciton will be related with the in-plane ones, Px and Py. And we'll see why that is important later on. This is the way I like to see Raman process. So we have the incident photon interacting with your lattice. It can create it or annihilate a phonon, and then we have the recombination. The Raman intensity is basically given by this equation over here, and we can have different resonance conditions, which can be satisfied by the incident photon or scattered photon. So basically, if I'm going to excite my material with a wavelength that is matching with the energy band gap, for instance. So, well, we learned this already with Cansado, but it is important to emphasize this as well. So we have different notations, Raman notations for monolayer and bilayer, so on. So this is phonon dispersion for monolayer MOS2. It was calculated by Yuan Shi, actually, didn't put it here. So we can see actually the Raman modes, and what we actually measure is what we call E prime and A1 prime, which I'll be calling A1E, 1-G, and A1G just for simplicity in this work. So these two first order modes, which is actually here because they are located at the gamma point, so it is only one phonon process. We can characterize the number of layers. So if you are synthesizing your sample by CVD or exfoliating, so I just need to take non-resonant Raman spectra, for instance, with this wavelength, and just to take the difference between this peak position, and I can identify my number of layers very easily, like 30 seconds, I can know. So the interesting part is that when I'm measuring, collecting the Raman spectrum, So this is a non-resonant Raman spectra for bulk MOS2. So when I excite it with this laser energy, I can only see the first order peaks over here and a small intensity band around 450. However, when I'm very close with the excitation energy, with the band gap of the material, sorry, I can see a lot of new features that are being enhanced by the double resonance conditions, for the resonance Raman conditions. And one of the questions was, can we explain and try to understand then? Why we can see this? What is actually the origin, for instance, of this funnel over here, this band, this one, and why, how this band behaves when you change the excitation energy? So the explanation, basically, there is, so here it is the in-plane, the first order modes, and we have this band over here that were very well known as two phonons from coming a contribution from the longitudinal acoustical phonon modes, which they were associated basically at the M point, just because of the frequency position matches very well. However, we do not have only contributions from the M point, but also for all this band over here, this dashed line between M and K, as I'm going to show you. So first, I will try to understand how these two phonon modes changes with the excitation energy, and later I'm going to try to explain the origin of this band. So that's what I did. So this is the resonant Raman spectra for MOS2 for different number of layers. So here is just some spectrum, but it was actually taken more than 30 spectra for each sample, so more than 100 actually. And we can see how the intensity of these bands actually are changing. As you can see, for instance, the intensity here completely inverted for this laser energy. And we were actually trying to understand how does it work. So we did it basically, it is what we call Raman excitation profile. And what we did was considering the intensity of this peak as a function of the laser energy. And what we got was this. So basically, what I'm seeing is the exciton, how these phonon modes are coupling with the electronic transition of the material. So I would say this case is the exciton-phonon coupling that I'm actually analyzing. So I can see quite well for bulk, for instance. Here is the A peak position, the A exciton energy matched with this peak. This one as well with the B exciton. And we can see that these are actually present for all the samples, but its intensity decreases considerably, a lot actually, when you are in bilayer and monolayer. And however, if you quite notice that the in-plane mode actually does not cope with this A and B excitons, actually. And however, we have a very high energy over here, a peak related with the higher energy, which is actually the C peak that we saw in Louis' paper. So this red line over here is basically just a fitting, considering all these matrix elements here constant, just to see this behavior. And here is just extracting the information for the position of the excitons, which is the energy over here, which actually matches quite well with the optical absorption. And this would be this term over here, which is related with the exciton-phonon coupling lifetime. And we did some calculations last year. Yuan Shi actually did it, right? Just contributed for the paper, to try to calculate it considering the matrix elements in this case. I wouldn't know how to explain how was actually the details for the DFT calculations, but we observed there is a very nice agreement between theory and experimental results. So what I'm going to show you to explain right now is actually quite matched with the theory. And how I can explain actually this behavior over here, why I do not see why this in-plane mode does not cope with the A and B exciton, only with the C exciton. However, the totally symmetric phonon mode with the A1G actually copes with the three A and B, A, B, C excitons. This is actually because of the symmetry of the orbitals and as well of the excitons. So actually the A1G mode copes with the A prime, with the A, B, and C excitons because it is modulated by this vibration. It's a totally symmetric mode. However, the C exciton only modulates, right, since they have a px and py orbitals. So there is a dependence of the exciton, the symmetry of the exciton, and symmetry of the phonons that will be modulated in this case. So this work was actually published in PRL, and it was the first work that systematically studied MOS2, which was an DMD for more than 30 excitational energies, and observed this kind of measurements. A few months later, there was a lot of papers on WS2, WSE2, and MOSE2, where they observed the same kind of results. But we were the first one to actually explain it. So what about this region over here, which between these two wavelengths, these two excitational energies, what is actually happening? And why is it interesting? It is because it is between mapping between the A and B excitons in the materials. So I wanted to see what exactly was happening. And the most important is that this band over here, which is a second order band, or double resonance band as I'm going to demonstrate, is actually only enhances considerably for this when you are, the excitational energy is very close to the A and B excitons. So this is a Raman map, basically, with several, more than 20, 25, I think, spectrums over here, between 1.80 until 1.18. So the spectrum was collected in a very small range, about 300 millieV. And we can see, actually, the first order modes over here. This would be like the E prime, and this would be the A1 prime, A1 E prime, in-plane and out-of-plane modes. And we saw that the Raman spectrum for a small range of energy changed considerably. And the most important is that we observed some new dispersive bands, and we didn't know how to explain that. So we wanted to understand why this band, for instance, this P1 peak, which is demonstrates the highest dispersion, what is the origin of this peak? And the most important is that this band over here actually is not a contribution only by the 2 LA at the M point, which was previously no, but actually there is a set of peaks over here that it is contributed. And then we made the question, can we actually explain which peak are this, which phonon it is involved, or actually in which place in the Brillouin from which point it's coming from? It is important to explain that since the 70s, 80s, this is only know that this band is 2LA, M, and it was an issue that was never answered until we actually published this paper 2 years ago. So we were actually the first one to explain the double resonance process in transition metal dichalcogenides, in semiconducting transition metal dichalcogenides. This is important. So basically, we are considering phonons that will be actually here at M and K. So the phonon branch that is participating in the process, it is the LA. And we took, after the feeding process, this is the Raman shift, the peak position of each one of these peaks as a function of the excitational energy. And we see that the P1 presents the highest dispersive behavior, and also one peak over here that I'm calling as P3. So why does it happen, and how can we explain this? So we made a model. We consider only the single particle because it was the easiest way to explain it, and consider similar the double resonance process for graphene, the same idea. So for higher energy, for instance, I would be in this point over here, and for lower energy would be quite below from the parabolic dispersion. So we considered this, and Iwanshi did some calculations to see from where the on-resonance electrons would be in the Brillouin zone. So he started to observe that the locus of here starts to expand outwards from the electron states when you are increasing the excitational energy. And we also calculated to observe which phonons would be participating. in these resonance conditions. And similar to the graphene case, they were actually at K and K prime points. So it was an interval scattering from K to K prime, which is, this is quite well known for graphene. And here we can see that the on-resonance phonons has a very strong contributions at the K point. So doing this is basically to explain is that we are mapping this around the K point, the phonon, the LA branch around the K point is moving away from K, something like this, as I'm explaining here, when you're increasing the excitational energy. And doing some calculations and just using this equation here, considering all the matrix elements constant, we were able to also get the peak positions of P2 and P3, and see that P3 actually presents a dispersive behavior, and it matches quite well over here. So this phonon is actually a contribution from the K point, around the K point, and this P2 does not change the position as a spectra, which is actually coming from a singularity, a Van Hove singularity between M and K points of the brilliance. And the only issue right now would be to explain this peak over here, which also shows a small dispersion, but it was not observed in the single layer calculation. To explain that, I need to look at bulk. So we did the same experiment, so for bulk case, and if you take a look right now, this Raman spectrum for this band actually changes a lot. So you see there is an inversion of intensity of this band and this one over here, sorry, this mode, these peaks over here, when you're increasing the excitational energy. So before I had only one highest intensity, what was around the B exciton. If you take a look, sorry, should just come back here. One maximum over here. However, now for bulk, we have actually two maximums here, and only one, which is the highest intensity, which is the P4 peak that we're not able to properly explain. So from where is it coming from? So we decided to see how is this behavior over here. So we have the 2LAK that we know, and this is the Raman spectrum for a different number of layers for this excitational energy. And we see that when you are decreasing the number of layers, we see that this peak actually completely disappears, almost disappears, right? So we see that this one is the most intensity one. However, for bilayers and bulk, there is the opposite behavior. Why? This is actually involving over here. This is actually involved due to the transition from the direct band gap in the material. So the phonon that's actually participating there, it is a phonon from K to Q stage over here. From K to Q, this, when you're decreasing the number of layers, this state over here, this goes up over here, as you can see. And actually, it is involving phonons that it is actually at the M point. So the highest frequency is actually related with 2LA phonon modes at the M point of the material. So we perform also see the on-phonon resonance and the electron, and we see that now we have a strong contribution at the M point of the material. And this perfectly matches with our experimental results. So we were able to explain the origin of this broad band around 450. We did the calculations and also the experiment for a defect band. So we got a monolayer MOS2 single layer irradiated to create defects, and we were able to see the heavy frequency of this band, which is over here, which is the LA band, like a D band in graphene. And we did all the procedures, measurements as well, and we got the same results, and which were matching with the calculation as well, to see the consistency of the work. If our explanation was actually made sense and we did it, so it made it actually. There is another funnel, just because I wanted to talk about a little bit about other works. The P1 peak was actually a puzzle, because what we're trying to do is try to see the phonon dispersion, see the frequency position, and try to correlate that to what we are seeing in our Raman spectrum. And there was actually, from the phonon dispersion, we came up with the idea that actually there was a paper into the materials that they did all the group theory about all the phonons that would be allowed by Raman spectroscopy. And there they say that would be LA and TA phonons. So we also did this calculation and observed that this combination of phonons actually also matches quite well. And here you can see that the LA actually is the dispersive band, and this one actually dies. It's almost constant, the TA. So one question that we made it recently was, okay, I'm in my lab. To see the resonance behavior, this dispersive behavior, actually I need to wavelengths that's very close across A and B excitons. And this is very hard to get because the energy difference was basically 300 millieV. And it's not everyone that has these tunable lasers to do that. So there is possible a way to try to observe or map the dispersive behavior by, I don't know, temperature perhaps, and that's what we did. So this is the Raman spectra for monolayer, MOS2, for different temperatures over here, for this excitation energy, to try to see how this band here actually changed. You see there is an inversion here. This peak starts to increase when decreasing the temperature. And this is the excitations for some wavelengths measurements we did it at the 80K, just to see how the spectra are actually changing. And here is just the fitting procedure we did it similar as that previous work in Nature Communication. And here is basically, the peak position as a function of the energy at 80K and at room temperature to just observe how actually the behavior were for each one of these temperatures. These open dots over here, squared and dots, are actually the results from from that Nature Communications paper, and it matches quite well with this experiment. So basically, we're asking, is it possible to correlate just measuring the PL spectrum and Raman for some excitation energy and try to see actually where my phonon is? So this is possible only for that P1 peak, the LA plus TA around the K point, because it presents a very high intensity. So what is this? This is basically the peak position, the laser energy difference between the excitation energy and this peak over here, the TA. So this is the PL spectrum we took at 173K. And here is just to demonstrate how this peaks behaviors when you are actually varying the temperature. This would be the charged exciton and trions and bound exciton that there is in MOS2. So one way right now that we try to figure out to see the dispersive behavior was actually combining Raman spectroscopy at low temperatures and the PL spectrum to just try to map. However, we got some issues over here, which is basically related with the how the broad of this band will change with the temperature as well. This paper just was published 2 weeks ago in Journal of Raman Spectroscopy. It is from Rafael. Okay. I know everyone's kind of tired, right? So I'm trying to move a little bit fast as well for questions. So, all right, we know everything right now. We made measurements, me and several students and postdocs at the lab by the time, and we now understand how is the Raman spectrum and the Raman bands for semiconducting TMDs. But they are stable. They have the hexagon 1H to 8 symmetry, basically. But how does it work, basically, when you are using a material which has low symmetry as well, which is the case from the rhenium diselenide, rhenium disulfide? When I say that, it's because from group theory, these materials, they have only two operator symmetry, which is the identity, the E, and the inversion as well. And the unit cell, there is a lot of atoms by unit cell. It's a completely and very complicated material to try to measure because it has an anisotropic properties as well. So depending on how one exciting the material, the orientation of the incoming beam, and also the scatter light, my spectrum will change completely. So at first we're trying to figure out the better way to try to do these measurements. Because if I'm doing measurements like today and I put the sample in a different position, even if it is just 1 degree, the sample will change. The spectrum will change, sorry. And one other issue is that the power that also, the laser power should be very low, otherwise you just burn your sample. Working with selenites is not, for this case, is kind of complicated as well, to not have some heat effect. So we decided to try to do is map the polarized Raman spectrum for these materials, for monolayer. We also have some results for bulk, but I'm not showing over here. And try to see if it is possible we observe all the peaks that are expected by group theory. Because none of the reports up to date, they have actually seen that. They just do some unpolarized actually measurements, like just rotating the light or just rotate the sample without to worry with the orientation of the incoming and the outgoing beam. And they say, okay, I got like 16 Raman spectrum, and that's all. I don't know where is the other 2. And we were trying to see if we were actually doing a properly Raman measurements, polarized Raman measurements, we could see that. So this is like the structure of the rhenium diselenide. You can see it's completely different from that case. And this is like a chain behavior, as you can see over here. This is actually indirect semiconductor with 1.3 EV in monolayer, which is completely different from MOS2 and the other semiconductor DMDs. And it has basically what they call 1T phase, where some say it's 1T, some say it's 1T prime. So there is this discussion, yeah. So how we got the sample was basically by exfoliation, which is the simplest way. We got some crystal from Mauricio Terrone's group at Penn State, and this is the sample we measured. If you're exfoliating this kind of sample, it always have this kind of behavior over here. You can see this shape, which is related actually with the symmetry from the material. So these have this laminar behavior. All the samples, rhenium diselenide, rhenium disulfide, will always be the same. And you can see over here. So over here, in this point, here, just a close-up, you can see it is a monolayer. And how we confirm that? We perform some low measurements, some Raman measurements for the low frequency modes. In this case, to characterize and actually see if it is a monolayer or not. So what we did this is actually the polarization of the both incident and scatter line. It is actually aligned along the edge of the sample, which is aligned with this edge over here. All right, so this is our 0 position, 0 degree, let's say like this. And we expected by group theory, because of the symmetry, they would have 18 Ag non-degenerated first order modes because of its low symmetry. And we were actually able to see all of them. For the first time, we were actually the first one to actually see all the 18 modes that was expected for this material. And I put it here. This is just, I will demonstrate later this equation. I think I put it in the wrong slide, but that's fine. So doing this, we can see there is several peaks. And the intensity for some of them are quite high. The other ones is very low. And we did it was basically, this is the Raman equation, the classical one for the Raman intensity. Here we have the Raman tensor, and this would be the incident and the scatter wave factors. And here we have it for parallel and perpendicular configurations. What we did it was basically consider the parallel, this one and this one over here, where we are considering this incident wave factors, incident and scatter ones, and for perpendicular, we are considering this one. Using this equation, put all of this here, we can get this kind of equations here. The Raman intensity for the parallel and perpendicular is quite simple, just algebra. And what we did as additional issue is that we know that there is interference effects from the substrate. And since we want to study and understand how this peaks behavior when you are changing the angle, it is important to see as well if the substrate it is kind of influencing in our spectrum. So what we did, we prepared 2 samples. One was on silicon and silicon dioxide, and another one was like a glass, a cover slip. And this is just a position for one of those peaks, which is this one over here, okay? And we got the intensity as a function of the angle rotating the sample. And we can see that there is a very nice agreement, doesn't change that much, but when you are summing the intensity, we see there is some interference. Some peaks are actually off this gray curve over here. However, for the cover slip, we do not see that kind of behavior. Some of these peaks are not out. It's very good agreement with this fit, which means that we are, in this case, do not have interference from your substrate. So since we wanted to study the intensity, and we do not want any kind of interference in this case, we decided to perform all the measurements in the cover slip, just for interference effect. Avoid that. So this is then the polarized Raman spectrum for two configurations, the parallel and perpendicular. So it is important to notice this is a configuration, parallel and perpendicular. So I'm just to change the incident and the outgoing are fixed. What I'm moving, rotating is actually my sample. All right, so I have that position. So it's a line here along this edge will be the 0, and I just rotate that 360 degrees actually, but here we just put it until 180 because it is just repeated itself. And we can see that the peak intensity for some of them considerably changed. For the parallel, as you can see here, for instance, this peak here, which is very high intensity, as you can see in this map, it actually changes intensity for the perpendicular configuration. And as well happens for some of the modes that were very low intensity here, actually starts to appear. For instance, look at this peak over here. For the perpendicular configuration, we actually see 3 peaks very well defined. However, for the parallel, we see only 2 of them. So we are actually increasing the intensity of a very small peak that is between these 2. So now it became more clear. So this actually can work as a Raman fingerprint to understand the intensity and analyze specific Raman modes in this kind of samples, doing polarization Raman experiments. Well, there was a lot of work in the literature about anisotropic materials, especially for black phosphorus, where they observed that the polarization when you're doing Raman polarization, you need to see how the Raman tensor is actually working. And actually, the Raman tensor, so this is the equation, this is the Raman tensor, considering the imaginary part, which plays an important role here in this case, since it is anisotropic materials. And we calculated the intensity. We just put this one of the equations, and considering these equations over here, we get the parallel and the perpendicular equations. We are considering imaginary complex Raman tensors, Raman values in this case. And we tried to do was basically to fit the data and see which was actually the better, if we have only complex or real part contributing for the polarization intensity in this case. And we see that when all the data fits very well when you're considering imaginary complex Raman tensor in this case, which is something that was expected since it was observed before for black phosphorus as well. So the issue is trying to actually see this for all of the peaks, which is very complex, and that's what we got. So this is just a different way to show the same data, the same results I'm showing here, just an angular plot basically. And we saw that for all the Raman modes, I think I just am showing some of them here because are 18, right? So they fit very well when you are considering the imaginary part of the Raman tensors. And why it is important to know this is very simple. It's because if you're doing some devices, you need to know what it is actually the better position you are doing with using this of their. You need to know the polarization of your incident light, and as well the polarization, the orientation of your sample. And of course, if you are considering there is a lot of optical effects happening as well, the complex values may be important, may play important role when you're using this kind of materials. All right, so okay, it was about 45 minutes, what was expected. So the summary was that we observed, we explained actually the double resonance process in monolayer and bulk, MOS2. We actually saw that the contribution of that broadband was coming from the K and K prime phonons near the K point, right? So an intervallic process between the K and K prime point, and also another process that is involving the K and Q phonon from here to here, which is actually coming from the M point. The transition from the indirect to direct band gap in MOS2 in semiconducting with H-phase transition method dipole coagenites can influence it's very helpful to try to understand the process. And also, we need a careful experimental setup when you are doing Raman measurements for anisotropic materials. So everyone that is involved in this work from UFMG, Marcos Piment was my advisor. So Leandro was here last week. It's a collaborator in this project and other ones in nonlinear optics. So Fantini, Rafael, who did the temperature measurements, he's a PhD student, is about to defend his thesis. Giovanni is a PhD student. I am his co-advisor in this project. Ariete, Andrej, and Leonardo, they are professor. This is a professor, and now Andrej is a postdoc under the supervision of, we're working with Ado Jório in TERS, which was the work that Cansado mentioned yesterday. From Penn State University, Yuanshu Wang, he did his PhD with CRASP, and now he's a postdoc there as well, Mauricio Terrones. And from the National Physical Laboratory, Sandra and Roy. Actually, Sandra now is in another university in Europe, I do not recall right now. And of course, the funding agencies. The work I have mentioned in here about the PRL and Nature Communications paper actually won the CAPES, our thesis last year. So it was something quite good for us, because by the time when I was trying to explain the double resonance process in MOS2, no one in my lab was believing in me. So it is something that I try to stick on, and it worked quite well, actually. So thank you very much for your attention. Open for questions. Oh, here. Okay, everyone understood?
Hi, so we were actually wondering about the theoretical approach used to model the exciton-phonon coupling